Okay, the second part of today's lesson is lesson 122. It's the last lesson of the year, and it's lesson 122, and we're talking about laws of logarithms, intersection and union of sets, and then Venn diagrams. All of this will be on the final exam. Let's see, we'll start out with the problems with the laws of logarithms, and actually we've been using these, but in order to do this, you need to remember that let's see, this will be given to you. B to the A is equal to M, and B to the C is equal to N. And this is called the exponential form of the equation, and we can write the logarithmic form, which would be log base B of M is equal to A, and log base B of N is equal to C. So what we're going to do is we're going to prove the laws of logarithms. So in this first one, it says we're supposed to show that the log base B of M times N is equal to the log base B of M plus the log base B of N. So in any kind of a show that problem or a proof problem, you pick one side of the equation to change and you make it look like the other one. So right here, we have M, but we know that M is equal to B to the A, so we can substitute B to the A. And we know that N is B to the C, so we can substitute B to the C. Like I said, we're only changing one side, so we're only going to work with one side. Now, these are both B's, okay? So that would be like x squared times x cubed. What do we do with the exponents? We add them, right? So that would be x to the fifth. So this would be log base B of B to the A plus C. All right, but here, because this base and this base are the same, these cancel out. So we're left with A plus C. That's where this comes in. A is the log base B of M plus C is the log base B of N. And there we have it. We just proved that law of logarithms. Okay, that's the product rule. All right, so the next one is the quotient rule. We're going to show that the log base B of M divided by N is equal to the log base B of M minus the log base B of N. So again, right here, we'll start out by substituting B to the A for M and B to the C for N. Okay, so if we had x to the fifth divided by x cubed, what would we do with the exponents? We would subtract, and it would be equal to x squared. So these are like bases, so we can rewrite this as log base B of B, subtract the exponent, so A minus C. But again, what happens to the log base B and the B? They cancel out. So we have A minus C left over. And back up to the top, A is equal to log base B of M minus C is log base B of N, which is exactly what we were supposed to show. So that's the quotient rule for exponents. All right, one more rule is the power rule. And what I mean by that is, for example, if we have x squared raised to the third power, what do we do with the exponents? We multiply, all right? So that's where we're going with this one. So this is, we're going to show that the log base B of M raised to the x power is actually equal to x times the log base B of M. Again, substitute for M. So remember, M was B to the A, and now it's being raised to the x power. Okay, well that's the same as saying log base B of B to the AX. And then what happens to the B's? It cancels. You have AX left over. And A, remember, was log base b of m, and then it's multiplied times x. We don't just put the x over here on the right-hand side because we're not taking the log base b of m times x. We're multiplying the x times the log base b of m. Okay, if you write the x over here on the right-hand side, it means you're actually taking the log of m times x, and that's not what we're doing. We're taking the log base b of m and multiplying it times x. Okay, so that's what we were supposed to show. All right, so that's all the laws of logarithms. So now you can feel comfortable that we're moving on to something else. So the symbol, this upside down U looking kind of thing, is for the intersection of sets. So remember, intersection would be only the elements that are common to both sets, or more than two sets if you're talking about more than two. The symbol that looks like a U is for union, which means you put everything in one set. Okay, so everything goes here. And then this one, only the common elements. All right, so if I give you set A is 1, 2, 3, 6, and 7, and I say that set B is 1, 3, 8, and 9, and I ask you to find A intersect B. You can always tell that the difference because the U goes for union. If it's not union, it's obviously intersect. So we're looking for the numbers that are common to both of these sets. All right? So there's a 1 here. Is there a 1 over here? Yes. So that's part of the intersection. Okay, there's a 2 here. Is there a 2 over here? No. So that's not part of the intersection. There's a 3 here and a 3 here. So yes, that is part of the intersection. Is there a 6 in both of them? No. Is there a 7 in both of them? And we can stop. We don't even have to look at B because we've already exhausted all of the possibilities for intersection. Okay, now, union, remember, I said, is put everything together. So if we wanted the union of those two sets, and you list them in numerical order, and you only list each element once. Okay, so we would put a 1, a 2, a 3, 6, 7, 8, and 9. That's all the elements that are in both of these sets. So that's for the union. All right, now that's in set notation. The last thing that we're going to cover for the semester is Venn diagrams. And Venn diagrams are named after Mr. Venn, who invented them. And they're circles. So what you have typically is you have this right here. It's in a rectangle. And this right here is called the universal set. Okay, so this would be everything in this box. And within the box, you have circles drawn. Okay? And we might have 2 or we might have 3, and they'll be labeled. So this would be like set A, set B, and set C. So if I ask you to graph A intersect B, that means that I want you to shade in everything that's common to set A and set B. So there's no set C here. So we don't have to worry about set C. Pretend it's not even there. Only look at set circle A and circle B. So the intersection of A and B would be this little region right here. Like I said, don't worry about C because we pretend that it's not even there. So A intersect B is the part of circle A and the part of circle B that are common to both of them. If I wanted the union of A and B, you have to do a separate diagram for each one of these kind of problems, guys. You can't put A union and A intersect B on the same graph. So A union B means everything in A and everything in B. Again, it doesn't make any mention of C, so we just ignore it. So A union B would be all of circle A and all of circle B. All right, so then what if we have B intersect C? So now we don't have any mention of A, so we can ignore it, pretend it's not there. And here we're looking for only the members that are common to both B and to C. So that would be this little wedge right here. Okay, that's B intersect C. All right, what if we had B union C? So that means put everything from B and everything from C. Ignore A, but all of circle B, even though it goes into A, it doesn't matter. It's all of circle B and all of circle C. All right, so I have one last problem for you. A intersect B intersect C. What would that look like? So that's got to be only the ones that are common to A and B and to C. So can you figure out which region that would be that's common to all three of those circles? Okay, did you shade this one right here? Just this little bitty piece down here. Those are the only points that are in both A, B, and C. All right, that's the end of the course for this semester. Thank you.